Welcome to Chapter 9. We are going to be looking at electrons and the periodic table in this chapter. We are going to get our first very brief but very sweet introduction to quantum mechanics in this chapter. So let's go ahead and jump right in. So we're going to, like I said just a second ago, we're going to take a brief look at the quantum mechanical model as well as the Bohr model of the atom. The quantum mechanical model is the one that is most commonly used today in science, but the Bohr model works really well. It's not correct. It's incorrect, actually, but it still works really well. And so it's very useful for explaining the different parts of the atom and how electrons are situated inside of the atom, but it's not actually correct. What these theories are trying to do is to explain the subatomic structure of atoms. And so before we can really dive into that, we need to talk about light, because light is really our only way, I shouldn't say the only way, but it is by far the most common and easiest way for us to interact with electrons. There are other ways too, but this is the most common way, and light is the most similar to electrons of things that we can interact with. Electrons are very, very tiny, and photons are very, very tiny. Light is very, very tiny. So thinking about light, understanding how light behaves is going to help us understand electrons as well. So when we're talking about light, we ask ourselves, what is it, first of all? Well, it's electromagnetic radiation, which you might have heard that phrase before, you might not. It just kind of depends on your, most likely who you had for a science teacher in high school, whether you've heard of the phrase electromagnetic radiation. And that's all light is. Light is not made up of matter. It has no mass. So things like protons, neutrons, and electrons have mass, but light does not. Light does not have mass. And for a very long time, it was thought that light was exclusively a wave of energy or radiation, that it was nothing but this wave of energy moving through space at a very high speed. That's what was thought for a very long time. To kind of hone in a little bit here on what we mean by a wave, and to be more specific as to what we're talking about when we say light is a wave, when it comes to waves, every wave is going to have a few distinct features. Every wave is going to have a wavelength, it's going to have a frequency, and it's going to have a speed. So let's look at each of those real briefly here. So every wave is going to have a wavelength, and the wavelength is pretty self-explanatory. It is the length of the wave. More specifically, from one point on the wave to the same point the next time the wave comes around. So for example here, from peak to peak. But this length here, the length from peak to peak, is the exact same as the length from the trough to trough. It's the exact same distance. It's just a little easier to see up here at the top. And technically it's the same from here to here as well, from the midpoint to midpoint. But you have to be looking at the midpoint where the wave is coming down. So it's not the same to here. That's just 1/2 of the wavelength. Because down in this direction the wave is going this direction, and this way it's coming up this direction. And so this is not the same point on the wave. Even though it's at the same y coordinate, it is not the same point on the wave, because the wave is moving in the opposite direction. So the wavelength is just that distance from one point to the same point the next time the wave comes around. I've already mentioned a few of these names here, but we have peaks. So every wave is going to have a peak, every wave is going to have a trough at the bottom, and every wave is going to move in a direction. It moves in a direction with very few exceptions. There is such a thing as a standing wave that does not actually move, but we are not going to talk about that here. All the waves we're going to look at move. They're what we're called traveling waves. Right. Every wave is also going to have a frequency. And the frequency is the number of times that a wave goes through its wavelength in a second. So the wave is moving along here, and it's going up and down and up and down and up and down and up and down. And so it's moving along at a certain speed, and every time it goes through one of its wavelengths, we make a count. So if I had done all of this in 1 second, which I know I didn't, but let's pretend that we did, if we counted how many wavelengths it went through in that second, we'd have 1, 2, 3, 4, 5 wavelengths in 1 second, and so this would have a frequency of 5. Frequencies are always written in some iterations per second. The units on frequency are always per second or per minute or per hour, just depending on how long it takes for the thing to happen. And the higher the frequency of the wave, the more energy the wave has. And hopefully this makes sense. If you're standing on the beach and you have, these nice soft waves coming in, every 30 seconds or so, those waves, coming in very separated, they're not going to have much of an effect on the beach. You could be standing there in the wave and it's not going to push you around a whole bunch. If, on the other hand, there's a storm coming in and it's pushing those waves up, and so instead of hitting a wave crest every 30 seconds, you're getting one like every 5 seconds. You're just wave after wave after wave after wave coming in and hitting you much faster than it was before. There's more energy in those waves. There's more energy per second that you're encountering because of those waves. And so the higher the frequency, the higher the energy. So then the last thing here that every wave is going to have is some speed, because again, we're always talking about traveling waves here. So they're always going to be traveling at some speed through space. And by space, I don't mean like literally outer space, although that is possible as well, but just through the space that we live in, through the universe. Things will always be moving at some speed. This will vary quite a bit depending on the wave that you're looking at. Some waves go really fast, and some go really slow. Excuse me. Sound waves, for example, travel at about 761 miles per hour, which, compared to us, that's really fast. Like, that's a really fast wave. But it is snail slow compared to light. Light doesn't move at 761 miles per hour. It moves at 3 times 10 to the 8 meters per second. So every second it is going, what would that be? 300,000 meters, I guess? Yeah, I believe that's correct. I think I'm doing that correctly in my head. Correct. Feel free to correct me if I'm wrong on that. 300,000 meters. Or sorry, 300 million. Sorry, I didn't do it right in my head. 300 million meters per second, which is a really, really fast speed. It is quite literally the fastest speed possible. Nothing can go faster than that. And if you're wondering, well, I think I saw an article a few years back and they said that they found something going faster than light, they were wrong. You see those articles pop up every once in a while. I remember seeing one when I was in high school and thinking, I guess that's cool. Something going faster than light, but I didn't think that was possible. And then I heard, a few months later, the people that had made that claim came back and said, oh, actually, we didn't do our measurements correctly. It was not going faster than light. There has never been anything discovered that moves faster than light. And as far as I'm aware, and as far as my scientific knowledge takes me, there never will be anything that moves faster than the speed of light. And I know this because if it was possible to move faster, light would move faster. Light moves as fast as anything in the universe is able to move. And if it was possible to move faster, light would move faster. because light has no mass, it doesn't have restrictions on its speed like other things, and it is able to go as fast as this is really, I know I'm getting kind of in the weeds here, and I apologize if you're like, oh, move on, but I think it's kind of cool. There's a thing called the speed of causality. There is a maximum amount, there's a maximum speed at which one thing can cause something else to happen. And light moves at that speed. It moves at the maximum possible speed that the universe can handle, that the universe allows. If the universe allowed something to move faster, then light would just move that speed. It is literally limited only by the universe itself, by the physical constants of the universe itself. And so even if somehow something changed and it was possible to move faster, well then light would then do that. It would go faster. So anyway, I think that's kind of cool. I think it's kind of cool. I would encourage you, if you're interested in those kind of things, there's some really cool YouTube channels out there. I think there's one called PBS Spacetime, where they talk about really complex stuff like this, and it's stuff that even goes over my head half the time or more than half the time, but it's still really cool to hear someone talk about it. Alright, so we've talked about waves, talked about the different parts of waves. Einstein, back in the early 20th century, discovered that what we had thought about light was not actually 100% correct. We had thought that light was only a wave, and Einstein showed that that's not actually the case. It is not just a wave. And that's where we're going to pick up in the next video. We're going to talk about photons, which are little particles of light, and we're going to talk about the electromagnetic spectrum and the characteristics of photons in each of these different regions on the electromagnetic spectrum. So I'll see you in that next video.